Okay, good morning everybody. I hope everyone's having a wonderful day. So I'm going to be picking up from where I was last day. We're going to be talking more about binary search, in particular its worst case time complexity. And then from there, we're going to just talk, I just want to wrap a couple of ideas in a bow for us. And then we're going to be moving on to talking about stacks and queues today. So last day I was trying to formulate what we call a recurrence relation that represents the time complexity of binary search. So I thought I would go into a few more details just to elaborate on what we discussed at the last bit of class last time. So just keep in mind that there's two big parts when we're actually analyzing a recursive algorithm. First, there's the non-recursive steps. So this is the amount of work that happens when you just make a call to your function. Now, depending on what the algorithm looks like, it might be more appropriate to just count all the operations, or it might be much easier just to count them when, in the worst case, you have the base case, and then count them when you have them in the recursive case, because these two can differ. In our example, it won't, but as we're going to see some more examples, it'll be sometimes where, in the recursive case, we count up all the non-recursive work. It's actually going to not be the same as the base case, because typically in the base case we're solving a very small version of the problem, and typically that will be the case that it takes constant time. Here it also happens to take constant time in the recursive case if I ignore the recursion, but that being said, it's not going to be like that always. I just want to give you a bit of a heads up on that. So recall last day we said that the worst case scenario for binary search is that when X is not in L. So the first step that we'll typically take when we analyze a recursive algorithm is we start off by ignoring the recursion. We look at a given call to the algorithm. So what we'll do is we count up the operations that happen for a given call. Typically, if there's a clear distinction between a base case and a recursive case, you'll count how many happen in the recursive case and how many happen in the worst case for your worst case scenario. So for example, with binary search, in the worst case, when the base case occurs, it only evaluates actually the if statement at the top of the algorithm when the two intervals cross each other, and it's actually successful in that case and it returns -1. Otherwise, it has that else block, right? But that's what the recursive case will do always. So keeping that in mind, in this example, it won't matter. You can count them all. It'll still give you the same outcome. But most certainly, the idea is that you want to count how many happen in the recursive situation, the non-recursive steps or work that occur in that recursive part. And then, of course, we need to incorporate the recursion. We need to understand how the recursion is happening. It generally will boil down to how many recursive calls happen, and how is that going to influence the size of the problem as it gets smaller. So how many recursive calls are happening? What's the size of the recursive call? How much smaller is it getting each time, for example? We know that typically it'll be the case that it goes down, it gets smaller. So notice that we made the observation last day that the recursive case makes one recursive call. So if that happens, it's either going to go to the left half or the right half. Now, I use the word half because it's not quite perfectly, I'm using air quotes here, but the idea is that we're halving the amount of elements we have left roughly. Now, I'm going to be making a simplifying assumption that both of these halves are going to be the same size, n-1/2. Last day I showed you how I came up with that number. So recall that if I have, at one time, say I have n elements that I'm considering. So suppose I have n elements right here. And say this is my guess right here. Say this is position mid. If I don't find a match right there, that means it's either going to be in this chunk or that chunk. So these are just subarrays, but I'm going to presume that they are of equal size, because if n, for example, is even or odd, that will change whether it's going to be exactly equal on both sides if I have n elements I'm considering. Do note that when I use n here, it's not necessarily the same as the length of the array. It's actually the number of elements that are going to be remaining for me to examine. So the idea will be, in the worst case, that n is going to eventually go down to 0, when I run out of elements to examine for binary search. So remember last day I showed you, hey look, if I have n elements, the middle one, I don't ever examine it again. So I have one less element, right? So there's one less element, but that means that if these are exactly of the same size, then that means that it's going to be how many elements I have left, n minus 1 of them, divided by 2, right? So that's where I get this from, right here. So I just explained that last day. So last day I came up with that right there. Now to put everything together that we have, we know that the non-recursive work that happens in the recursive case, so if I count up all the operations that happen when I ignore the recursion, in that recursive case, it's going to be some constant number of operations. You could give that a name. You could call it like C1 or C2, most certainly. For simplicity, I'm just going to call it 1 because I know that it's anyway going to end up being some constant number of operations. It's just going to make my analysis a little easier to do, but most certainly you could do the exact same exercise having two constants like a C1 and a C2, where C1 is the number of operations that happen in the base case, and say C2 is the number of operations that happen in the recursive case, for example. So I'm going to let T be our complexity function that represents the worst case running time of binary search. Now I put all of these facts together. Remember, I have my recursive case and my base case. You may have multiple base cases, that's fine. So we know in the base case there's a constant number of operations that happen. Like I said, you could call this like C1 here instead of 1 if you like. It doesn't matter in our case because it's still going to be a constant number of operations regardless. And in our recursive case, we have one recursive call. That's what this represents. Notice that the size here, the input of this is actually the number of elements I have to examine. So it goes down from n to n minus 1 over 2. But I do one recursive call. So that's what this represents. And the amount of non-recursive work that happens in the recursive case is some constant number of operations. I could call that, for example, C2 if I wanted to, or even C1 plus C2 if I really wanted to be very generous. Either way, it's just going to be some constant number of operations. So this is how I'm going to formulate my recurrence relation. So this represents the worst case running time of binary search. And now, this is the thing that's a little bit different about this one. Notice that this is not just simply just a straight formula where I could just straight up just examine it and simplify it down, right? Now, of course, you can do that with this. I'm going to be showing you one technique for achieving this today. I will post at some point some more examples of using this technique. But for the sake of this, I'm going to walk you through what I would consider a bit more of a challenging example of using this approach. So what I'm going to do now is I'm going to do what we call solving this recurrence relation. Now, solving is a little bit misleading. Solving in this context means I'm going to make this recurrence relation. I'm going to take this and I want to represent it in a way that would be easy for us to determine the asymptotic running time. So instead of it just simply being, oh, there's this recursive part here, notice that this is actually in terms of the function itself, just like the recursive algorithm, right? That's not a coincidence. It's a really nice natural way of representing it. Like I said the other day, it's like you're simulating the running time using this recurrence relation. So if you have that intuition for this, you're really well on track. So you can imagine this like this is actually us counting the operations now of a smaller subproblem when that recursion occurs in the recursive case. So the whole idea is that eventually it will become where I have no more elements left to consider. The base case. So that being said, what we want to do is we want to turn this into something like a closed form expression or just a simplified expression that I can easily determine the big O for. So that's what the goal of solving this recurrence relation will be, is I'm going to put it into a form that has none of this recursive part of it in this recurrence relation. It's just going to be straight terms, and the idea will be that we're going to try to find a pattern. So let's head over here. Let's go over here. So the technique I'll be using here is often called iterative substitution or repeated substitution. And the idea is that you try to study the recurrence by repeatedly substituting in its definition recursively to try to find a pattern. there's at least a couple different ways you could do this. For example, you could write out what t of n is, and then write out what that is. Then you could expand, or you could write out what, say, that is. Then you could write out whatever this is for this recursive part over and over again. Try to see if you can find a pattern. Because at the end of the day, we know what t of 0 is, right? Just like when I try to use binary search, I know that some constant number of operations happens in the base case, right? You could do that. Another way is that you could just write out what this would be as you decrement, just like I'm going to do here. And you try to see if there's a pattern that you can easily back substitute into the equation upwards from the base case. So for example, you could start off at t of 0, then go to t of whatever would be the next increment. So if we had, say, going from n down to 0, and it's being decremented by 1, for example, each time, you may have it where you figure out what a pattern would look like by just writing out what each equation is. And then you would start off at t of 0, then you try substituting t of 0 into t of 1 by just simply including it each time, and you try to find you try to use the guess of your pattern to come up with your general expression for t of n where it has no recursion in it. There is no recursive part to it. Now, what I'm going to do here with you is I'm going to try to find a pattern by expanding the recursive part of this recurrence by writing each time a new equation. So I want to keep track of how many equations I write down when I do this. But I'm going to do this until I reach the base case. Now, I'm going to have to study what the input of each one of these calls looks like. And the goal will be is to figure out when the input becomes 0. This won't necessarily be the same way you might apply repeated substitution in other circumstances, but I will argue that this is one of the more trickier ways of doing this. So I wanted to illustrate it here for you. So remember, this is our recursive part of the definition of t of n. This is when n is greater than 0. So remember, this is just the definition. Notice that I have, this is my recursive part. This is the recursive call. This represents our recursive call. So what I want to do is I want to see how many times the recursive call occurs. This is what this represents in our recurrence relation over here. So I want to see how many times that happens. So that's going to play a very key role in this analysis. So all I'm going to do is I'm going to write out what this means. So the first thing you might say, Dan, well, this is t of n. This is t of n minus 1 over 2. So everywhere where you had an n in this definition, you're going to write n minus 1 over 2. If it becomes a little bit tricky to keep a track of this, imagine instead of this being, say for example, an n, think of this like an apple or something. I don't know, banana. So I have t of a banana. And you know it's going to be t of a banana minus 1 over 2. So wherever, if you gave me t of banana minus 1 over 2, everywhere where you have this right here is going to be wherever banana would have been before. So it's going to be t of banana minus 1 over 2 minus 1 all over 2, like this. So don't let the fact that there's an n there throw you off. It's just that whatever the input is that's what's going to get replaced here in this case. So notice that it's n minus 1 over 2. Everywhere where I had n in my definition, because this is the definition of the recursive case, I'm going to replace that wherever n was with n minus 1 over 2. So the thing that we're going to do here is we're going to try to use some intuition to figure out a pattern. Now, I'll give you a heads up. I've worked this out a little bit more carefully so that we don't have to go into too many details here for the sake of time. But you'll find very often when you go through this kind of exercise that you're going to try writing out a bunch of equations and try to see if you can find a pattern. It won't necessarily click immediately like this. So I'm writing it, we'll tell you up front, I'm writing this in a way that's deliberately trying to show you the pattern. So when I do in fact write this out in the input here, just like, because that's what this means, notice that each time I do this, I'm going to add 1 each time. And I would like to know how many 1s there might be eventually when I get to t of 0. But when I simplify this down, you'll notice that when I, say, try to divide this through like this, you'll notice that when I try to make this all a common denominator, whatever's sitting right here actually gets bumped up by a power of 2. So what I mean by this is, notice I have n minus 1 over 2 minus 1 divided by 2. If I try to divide through, notice that if I tried to make this n over 1 over 4, for example, to make a common denominator here, it would have to be that this goes up by a factor of 2. So I end up with n minus 1 minus 2. So this minus 1 becomes a 2 now. And then I have 2 squared, so that is 4. That's me just carrying through the division here to make sure it's a common divider. Well, sorry, common denominator. But notice that, so I'm going to give you a bit of a heads up. Recall that 1 is 2 to the power of 0. You're going to see that every time I'm going to apply this definition here, by writing out a new equation, each time it's going to actually increase the power by another factor of 2 in the denominator. So I want you to keep an eye on that. So I'm going to write this out deliberately like this. N minus 2 to the power of 0, which is 1. 2 to the power of 1 is 2. And I have this 2 squared here, and I'm adding the 1 here. So I'm going to just see what this recursive part here does of the recurrence relation. So I'm just going to write a new equation out. And let's take a look at what happens. So if I apply the same thing, remember, just think of it like this is my input now. I'm going to put that wherever n minus, so when I have n minus 1 over 2 here, this all here goes where this is right here. Just think of it like the banana if it gets really daunting looking. But I worked it out a little bit here for you. By the same matter of intuition, you'll notice that if you carry out the division with this, you'll increase the denominator by a power of 2. And that means that whatever's sitting on the furthest right in my definition here, notice that remember, just like I had here, this minus 1 here, you'll have a minus 1 again, but that will actually go up by a power of at least a factor of 2 this time, because notice that it's 2 squared here as opposed to 2. So instead of it being 2, it'll be 4 this time. So this is actually what the form of this would take on when I put the substitution in on this equation. So if I just write out what this is, I end up with this. But notice each time I write out the next equation, the input gets smaller, right? It gets smaller. So I can keep doing this, but I want to try to make a guess of the pattern here. So notice each time I apply this recursive definition, so notice that this is the definition of the recursive part of the recurrence relation. Each time I write out an equation for the recursive part of the recurrence relation, notice that each time, notice this goes up, this is 2 to the power of 1. That's 2 to the power of 2. But notice in the numerator, every time I write out the next one, notice that the highest power in the numerator for a power of 2 is always 1 less than the 1 in the denominator. Do you notice that? So notice it's n minus 2 to the power of 0 minus 2 to the power of 1 minus 2 to the power of 2 over 2 to the power of 3. It's always one less than the numerator for the powers of 2 there. But the denominator always has one that's just one bigger. So I'm going to guess a general pattern for this. So this is the guess part of this process. So repeated substitution, sometimes it's called guess and check, because the idea is that you're guessing the pattern based on repeatedly applying the recursive definition by writing out new equations. So sometimes you actually use them, like I mentioned earlier, to back substitute into the equations working bottom up from the base case up. In this case, I'm just focusing in on the input, and I want to see what happens. I want to see when does it become t of 0. So we're working our way towards that. So notice that if I guess the pattern of how much it's shrinking each time, I have n minus 2 to the power of 0, 2 to the power of 1, all the way down. Keep doing differences until I have 2 to the power of j. And then I have the denominator being 1 higher than that. Well, if my guess is correct, which if we talked about mathematical induction, for example, you could actually verify this for yourself more formally. But for the sake of the discussion in this course, we're going to focus primarily on just deriving the pattern. So I have 2 to the power of 0, 2 to the power of 1. Notice it will have to be 1 higher, because notice that that's the same thing that happens here, right? It goes up by another power of 2 here. It goes 1 higher. And this will be 1 higher than whatever that is. So I have 2 to the power of j plus 2 in the denominator, and I have add 1 here. So one thing I want you to notice very carefully is how many equations I wrote out here. So notice that this is the definition. The first equation I wrote out for the recursive part is right here. This is the second one. Notice that the denominator here actually helps you know how many that I've written down beyond the definition here. Notice the denominator here is j plus 1. I want you to keep that in mind. So this is equation number j plus 1. So now what I would like to do is I would like to know when this input eventually, when I pick the appropriate j, the input becomes 0, because that's when we reach the base case. So let's take a look and see when that happens. So we're going to use these bits and pieces in a bit, but I want to look specifically at what's happening here at the recursive part, what the input is. So let's take a look at that. Okay, so we know that the input will always, like our guess, like I can confirm for you that that is in fact going to be the pattern. If you aren't convinced by this, just write out more of these equations. But we know, let me just recap what I just said. The input value given to t, on the left-hand side of the equation, decreases with each new equation, right? With each new equation. We stop this process of rewriting the equations. Like, I could keep doing this, but I don't know when it happens. We're trying to find out that. Because if you actually think about it carefully, if I told you that that recursive part represents our one recursive call, and the size of the input is actually how many elements you're considering at each time, what we're actually doing is trying to determine how many calls actually happen in binary search. Or at least we're trying to find a nice bound on that. So we stop this process. When we reach t of 0, right? Because that's the base case. Specifically, this is when, so if, notice our pattern of the input for each one of our equations. I had a pattern here that n minus 2 to the power of 0, minus 2 to the power of 1, minus 2 squared, and so on up to 2 to the power of j, over 2 to the power of j plus 1. I want to know when that's equal to 0. So let's find out that. So this is kind of the big trick with this, is I want to know specifically when this to the power of j plus 1 over 2 to the power of j plus 2 is equal to 0. Now you might ask, Dan, why is it this one specifically? It's because imagine I wrote out equation j plus 1. The recursive part as input is this. So I would like to know when this is actually going to be equal to 0, so that when I write out equation j plus 1, it's going to be t of 0 plus 1. So here's the fun thing, and you're going to first look at this and be like, Dan, how the heck are we going to do things here? Now, this is the lovely majesty of algebra here. Notice that I have a 0 on this side, and I have this in the denominator. You might say, Dan, what are we going to do with that? I'm just going to multiply both sides by 2 to the power of j plus 2. Notice that 0 is on this side, so it's just going to eliminate that entirely. So this is not really any different than me just simply considering when I take the numerator of this and I assign that to be equal to 0. But here's the thing. If I want to solve for n, because it seems like that's really what we want, and we want to know something about n here. Because J is really just the you've got to think of J more like how we're actually playing out the recursion. It's how many times it's happening. Instead, I want it in terms of n because n relates to our input size, right? It's the number of elements we're examining. N goes down in terms of the algorithm, if we think about it from the recurrence relation over here, but n is still the length of the array initially, right? So I would like to have some way of coming up with a relationship between this j and n. Well, like I said, you could just multiply both sides of this equation by 2 to the power of j plus 2. Then you'll notice that I could just simply move all these terms right here to the right-hand side by adding it to both sides of the equation. And you end up with as follows. Actually, let me take you one step further. Before we do that, I want to kind of put this together. So remember, each time I write one of those equations, I'm going to add 1 each time, right? I want to know how many times I do this. So I know this happens when the input looks like this on the j plus 1 equation. So I want to just give you an idea where we're going with this. Then, when I actually want to write this out without any of the recursive part or any recursion appearing in the recurrence relation, it's just going to be an expression that represents the total number of operations that happen. It'll look like this instead. 1 plus 1 plus 1. Where that last call, like I said, on the j plus 1th equation, it's going to be t of n minus 2 to the power of 0 minus 2 to the power of 1, all the way up to the power of j plus 1, all divided by 2 to the power of j plus 2. The one I'm referring to right here. I'm going to add 1 to this. Remember, that's the definition, just me applying it for the j plus 1 equation. So now the natural question becomes, okay, so when I do this, remember, I want when this is equal to 0, right? So I'll end up with 1 plus a whole bunch of 1s plus t of 0 plus 1. And then you ask, okay, so how many 1s are there? Well, notice that because of the number of equations I write down, notice that there's going to be j plus 1 of these. So j plus 1 many of those, because that's how many equations so remember, I have the initial call that happens. Remember the definition of the recursive part here. Then I have j plus 1 there's j plus 1 equations for which the j plus 1 equation is this one right here. So there's j plus 1 many 1s here. Then I just group this all together. I end up with a whole bunch of 1s again. Plus 1 plus t of 0. And all of this, there's j plus 2 many of these. I just kind of grouped that. Took that 1 out here, which shouldn't be very surprising given the denominator here is j plus 2. But let's take a look at this carefully here. So I have t of 0. Now remember, t of 0 is equal to 1, right? So that means, so what does this mean? This means if we want to come up with our solution, or when we solve the recurrence relation, i.e. it's just the expression that represents as a function of n with the same value of the recurrence relation, it'll be j plus 2 plus 1. I'm going to keep this plus 1 just outside of here just to keep things a little easier for me to play around with. So, to determine the value for j, because now I need to figure out what j is. So now this is where I wanted to go with this. So I wanted to contextualize what we're going to do with this. So now I have something that directly relates n with j. So watch this. So I'm just going to take my equation up here. I'm just going to call this star. But by star, by the same rationale I just explained a moment ago, I can rewrite this equation as follows. N is equal to the power of 0 plus 2 to the power of 1 plus 2 to the power of j plus 1. Which, if you actually rewrite this, you can actually rewrite this as a summation. You end up with the sum as from I is equal to 0 to j plus 1 of 2 to the power of I. Now, a question for you. What kind of series is this? What kind of series is that? Well, it's actually just a finite geometric series, right? So if you actually take a look at this, this is actually just going to be equal to 2. So this is specifically a finite geometric series. So it actually has a closed form expression. You'll find it in the list of closed form expressions I've given you in one of my documents on the course website for the Mathematics for Algorithms Analysis. It's this one right here. So I'm just going to apply it like so. And of course, this simplifies to 2 to the power of j plus 2 minus 1. So just to be very clear, what I did here, this is a finite geometric series that I applied. Well, the closed form for it, to be a bit more precise. So this is the finite geometric series when the constant r in this closed form expression is 2. I find an easy way to remember it is that whatever the highest value this takes on, j plus 1, it's always going to be 1 higher than that, and you subtract 1 from it. So it'd be 2 to the power of whatever that is to its highest, add 1 to that, minus 1. 1 to the exponent. But anyways, you'll notice very nicely, now I have a relationship between n and j that is something a little bit more explicit and fun to play around with. So let's see what we can do with this. So the first thing I'm going to do is I'm going to move this minus 1 to the opposing side. So I have just n with a something, and I have that exponent sitting on the, that exponential term on the right-hand side. So let's head over here. Let's head over here. The camera, come on, come with me, come with me. It was just hanging on out over there in the corner. We got to welcome the camera over. So let's see what we could do with this. So we're going to use a trick that we're going to use at least a couple more times in this course. So I'm just going to move that minus 1 onto the left-hand side. So move minus 1 to the left-hand side, right? Left-hand side. Then we're going to apply logarithms to both sides. Specifically, we're going to use log base 2. Apply logs to both sides. And so remember, the equation in mind is n plus 1 is equal to 2 to the power of j plus 2. So when I do this, you'll see I have log base 2 of n plus 1 is equal to log base 2 of 2 to the power of j plus 2. Now for those that know their properties of logarithms, you might know very quickly that, hey, look, I have something, like I have this, but it has an exponent here. I can drop that exponent out at front due to the power law of logarithms. So using the power law of logarithms, or power rule of logarithms, I could pull this out front as a multiplicative factor. So it's j plus 2 times log base 2 of 2. And what's log base 2 of 2? What is that? It's just 1, right? Because you can ask, okay, if I have 2 to the what is equal to 2? Well, this would just be 1, right? So that's just 1, which means that log base 2 of n plus 1 is exactly equal to j plus 2. So, putting this all together now, remember, we've established, remember that t of n, so recall, t of n is equal to j plus 2 plus 1. And we know j plus 2 is actually equal to log base 2 of n plus 1, right? So I'm just going to put that in. So then I can say, therefore, I'll make a note here. So we replace j plus 2 with log base 2 of n plus 1. Therefore, here's our expression, our solution to the recurrence relation. T of n is equal to log base 2 of n plus 1 plus 1. Well, what is this in terms of big O? It's actually big O of log n. It's big O of log n. You'll notice very often I will actually explicitly not write the base because the base actually doesn't matter. This is due to the change of base formula you might be familiar with. But sometimes it might be relevant for me to note it, so sometimes I will, sometimes I won't. So anyways, that is how we can analyze binary search. So I want to bring up one other detail for us. So this is how we know binary search actually takes big O of log n, which is much better than big O of n. In fact, it's much, much better. If you think of it, remember that an exponential function grows very quickly. The logarithm is you can think of it as the inverse of sorts of the exponential function, so it goes very slowly. That's going to grow much slower than just a linear term. So n versus log n, that's going to be much, much better. So anyways, I want to make one remark about space complexity. I'll have more details about this in the notes, so I'll ask you to take a peek in the notes. So just see the notes. I want to talk about the recursive implementation of binary search if we just presume what we've talked about with the call stack. So remember that what we've just established is that the number of recursive calls that happens is going to be logarithmic. It's going to be big O of log n because each one of my calls takes constant time, right? So, but notice that every time I make a call, there's actually a constant number of variables in each function call, right? So that means that if you think about how much space gets used by the algorithm, well, each time I create a new activation record, each time I make a recursive call, right? So at most, what's going to happen is for each one of the recursive calls, some constant number of variables get introduced. So if you think of the recursive version of binary search, what happens is each time I make one of these recursive calls, each one of the calls uses big O of 1 space. But the thing is the question of how tall does the call stack get? And what we actually addressed implicitly in this analysis is that this call stack actually becomes no taller than big O of log n. So that means that our recursive version of binary search, the recursive version, uses big O of log n extra space. Due to the call stack. So remember, each one of these uses some constant number of variables. That means it's going to take a constant amount of space each call. There's a logarithmic number of calls that happen. I must stress again that many compilers are capable of optimizing code akin to the kinds of forms that things like our recursive version of binary search take. But just to contrast this, the iterative version, notice it does not use multiple recursive calls. It only has one, and it also only uses a constant number of variables, if you recall it from 115. And it just has a lower and upper bound, and it changes those as it narrows while you go through a loop, right? Go through a while loop. Well, notice in that case, you have a constant number of variables, so you're not going to end up using a whole lot of extra space. You're just going to have big O of 1 extra space. So in this case, because we know how to write out binary search without using any recursion, nor emulating the call stack, we could actually speed up, well, not speed up, we could improve the space complexity, or i.e. the extra space that gets used for its iterative counterpart over its recursive one. So I felt like I wanted to mention that to you. So in some circumstances, if you can refine the algorithm so it doesn't need to use recursion, but it doesn't overly bear on memory, it might be advantageous to use the iterative counterpart over the recursive one. But like I said, there's a lot of things compilers do that I cannot talk about here. But the big thing is that you can always rewrite binary search akin to the one that you've seen in 115 in a similar exercise that we did earlier on. You'd end up improving the extra space usage. Okay, so that's all I have to really say about binary search, except for one thing. One thing I do want to note, as I mentioned last day, there will be actually some code in the notes if you want to try playing around with the recursive version of binary search. I have it in the notes, a full C++ implementation. And likewise, I also contrast the idea of a driver function versus the actual recursive algorithms implementation. So I encourage you to take a look at that so you get an idea of what a driver function is versus the recursive algorithms implementation. Remember, the driver function's job is just to set up the initial parameters for the recursive algorithm. It'll be often that the driver function will have the same parameters for your given problem. So I wanted to just make one remark before we proceed to our next topic. I wanted to talk just about comparing algorithms, because we've been talking about this for actually quite some time. I thought I would just illustrate how the big O is very useful for us to talk about comparing running times. And how I want to kind of put this all in a nice bow for us together. So I just want to compare the complexities of linear search versus binary search. So comparing complexities, because I haven't really explicitly said, oh yeah, if this one has this big O and this one has that big O, what does it mean in terms of efficiency for solving a problem? I want to address that right now. Let us compare binary search and linear search for the special case, a special case of the search problem, where array L is sorted. Because remember, that's when we could use binary search, right? So I just want to remind you that when we talk about the complexity function and the one we derive, we could have derived it at least a few different ways. We could come up with some complexity function. But the thing is, we talked about big O, right? So I want to suppose that there's two complexity functions. Suppose that the one that I have here for binary search is called T2. And suppose that I came up with a complexity function for linear search called T1. See, this is something I've derived through my worst case analysis. And keep in mind that if I choose to rewrite linear search in a different way, or I have one given implementation, which means that if I think of any one fixed computer or fixed machine, it'll have different constants. So when we came up with those constants, they might differ from machine to machine and implementation to implementation. But I must stress that when I talk about implementation, I'm talking specifically about the setup of the data structures and algorithms for that given setup of the algorithm. Because if I switch out different data structures, the efficiency will or possibly will change. I'm talking specifically how, when we take the algorithm, we implement it on the computer. When we go between different computers, the specs of that machine will differ. The compiler might differ. The point is that we're trying to ultimately understand the complexity of it. So remember, if I give you T1, I know that this is big O of n, right? We established that earlier. So likewise, we know that T2 is big O of log n. Now, I could get very formal about this and write out these in terms of sets. Instead, I'll draw you a picture that represents these sets. So this first outermost one is big O of n. So this will consist of complexity functions such as n. It'll also have ones like T1. It'll have, we could put like n plus 1,000 in here. It could be like 2 times n. I think we talked about this the other day. But within this one, because I talked about containment of these different complexity classes, I have big O of log n. So for example, log n plus 1 is in here. 2 log plus 2 is in here. Sorry, 2 log n plus 2 is in here. Many, many logarithmic functions in here. There's going to be many functions that exist within these sets. There's infinitely many of them. But this also will include T2 in here. But here's the thing. What is T2? T2 is the running time of every implementation of binary search. That's the big thing. Remember, that's the big thing. So notice that T2 is in this bubble. T1 is not within this bubble. It's not in here. It's not in big O of log n. In fact, you can sit down and actually prove this using the techniques that we've talked about. So if I wanted to, so remember, T1 is outside of here. But remember, T2 represents, there's going to be many, many different functions depending on what the constants are for your complexity function. They're all going to be within this bubble here, but they're not going to be outside of this bubble. They're always within that bubble. Likewise, if I give you the worst case running time of linear search, it's going to be outside of this bubble, but not within the bubble. But for some instances, it might be somewhere within here too. But the thing is, in the worst case, it's still certainly outside of this bubble. So when I say this, whenever I give you any one complexity function for my binary search, it's always going to be more efficient than the one for linear search in the worst case. So we can say a binary search is more efficient than linear search. Because it's possible for T1 to be outside of this bubble, and most certainly in the worst case, it will be. Because remember, I ultimately want to know how much time is required to solve the problem. And unfortunately, in the worst case, it's definitely going to be out here. It's not inside there. So that being said, that's really the big thing I wanted to touch upon when we compare two algorithms. So when we look at our big O's, what will happen is we can compare the two, and we'll see which one is better. And that's how often we'll compare two different algorithms. And I will tell you up in advance, when we start talking about data structures, because they'll consist of multiple operations, we'll see that there's going to be benefits and costs to having certain operations performing in certain ways. Certain data structures will have pros and cons to using them. So sometimes you have to consider in practice, do you only want to use a certain set of operations, or are you going to do this other operation that might be a little bit more expensive less often? These are things to consider, but in other cases, we might find the sweet spot for which we could do it as efficiently as may be possible in many cases. Sometimes not so much, but we can do pretty good. So anyways, we're going to switch gears, and now we're going to talk about a new topic. So that's going to conclude all my discussion about analysis of algorithms. So we're going to start now talking about some different topics now. Now we're going to start talking about stacks and queues. We'll come back to, we're going to revisit recursion in due time. But let's start talking about stacks and queues. Now, we've already actually talked about stacks already, but I feel like I want to give us kind of a better look at these things. So let's talk about stacks and queues. So the first thing I want to do is I want to define something called a container. We're going to talk about stacks and queues. So depending on how far along we get today, we'll see how far along we get. We might start talking about queues next day. So we're going to be talking about two kinds of things called containers. So a container is a data structure that stores a collection of elements. So we're going to study two different kinds of containers the next couple of lectures, either today, next class probably. So stacks and queues are two such containers, and they're very effective for modeling some basic procedures and different kind of processes. So, for example, earlier on in the course, I defined what a stack is. We'll come back, we're going to revisit that in a little bit here. And it is, for example, what we call a LIFO-based structure. So what it will do is, I want to talk about these two things. So there's going to be kind of two common patterns we're going to have. So around the beginning of this course, I talked about what LIFO means, last in, first out. There's also another notion called FIFO, first in, first out. So we're going to have containers that follow these rules for insertion and removal. So LIFO, so this is just a reminder, this is last in, first out. This is what stacks obey. So we've actually seen some examples of where you would have this as a fundamental process. For example, we talked about the call stack. A call stack is a good example of where you might run into modeling a given problem using a stack or a given system. Another way you can also run into a stack very often is through retracing steps in a search. So for example, if you wanted to try solving a maze, a stack data structure is rather effective at doing this. In fact, you can get much more general with the structure of how you might search a maze using the technique called backtracking. And it actually uses recursion, which uses the call stack. But generally, it's good for coming back to things after you've tried everything, or it's also good for unwinding steps that you've made. So you might know of something like an undo feature. Some programs have an undo feature. So say if you have a sequence of actions, say think of something like a word processor, and you'd say type in some words and you want to go back to the state of the program for which you didn't type in those few words, you can use an undo feature. So what the program might do is it might maintain a data structure that stores the state of the program up to some point or certain parts of it that are relevant. And the idea is that you just simply, whenever you want to go back to the previous state, you just pop the stack. You can go unwind those steps, and whenever you create a new state that you want to keep track of, you push that onto the stack. So it's very common places where you run into this using a stack, this LIFO, like rules for insertion and removal. A queue, as the name suggests, it's very natural to think of in terms of lines and things like queuing processes, which I will keep rather general for the sake of our discussion, because they can mean all sorts of different things. For example, you may have a buffer that consists of a whole bunch of things that need to get processed. And the idea is that a queue can be one way to model this. So you have a whole bunch of stuff that needs to get processed, but it comes in a very specific order. Whichever comes in first needs to get processed first. Hence why we call it first in, first out. So very often, queuing processes, which you can think of just like if you have a whole bunch of people standing in a line, the idea would be that when people enter the line, the person that enters the line first gets served first. So one remark I want to make is that whenever we have an array-based implementation of these data structures, I'm going to have a constant that's going to be kicking around that I will have the ability to modify at some point. Now, it's not really a constant, but most certainly when you actually implement it, it won't necessarily be a constant, but we can think of it like a constant. So something that we'll have as a capacity for the array. So like it won't be a literal constant in your computer program, but it will be a constant that you fix at the beginning, but it will get modified in some way as the data structure gets modified. So it's usually meant to be the capacity of how many elements you're allowed to have in the array. So note, assume n is so capital N is the capacity of an array for array-based implementations, because this is going to be relevant for us. Because there's going to be two distinctions here. There's going to be how much you can fit into the array, capital N, and how many elements there actually are in our data structure, lowercase n. So sometimes the worst case running time will actually depend on capital N, other times it will depend actually on lowercase n. So sometimes when you pick capital N, it actually has some practical consequences for how you pick it. So for the sake of our discussions here, I'll assume that this capital N is large enough. I'll talk more about it when we start talking about the time complexities. So in practice, you normally try to make sure that this capital N is big enough so you can fit everything you need into the data structure. But if you can't, one thing I do want to make a note of is you can always take a given array and you can create a new array and you can copy all of the elements of your array, put them into the new longer array. So I'll talk more about that as we come along. I'll also include an example of how you might do this resizing process. So the idea would just be you have your array, you create a new array that's maybe twice as long, for example, and then what you do is you go through your old array, copy all of its elements left to right into the array, the new array, and then you reassign the array's pointer to be the new array. We're expanding its capacity. So let's talk about a stack again. So I want to talk about a stack. Yeah, we'll probably just talk about stacks here today. We'll probably talk about queues next day. So I just want to remind you about how a stack works. We'll talk about the stack ADT and some common operations I want you to be aware of for the stack. And remember, it's an abstract data type, so you can actually have other operations. You can also define other operations. These aren't the only ones you can have for a stack, but these are very common definitions for the operations for a given stack. So let's talk about a stack. I'm going to remind you what the stack ADT is. So in the context of what a stack is a container. is a container that follows last in, first out. First out, which we called LIFO, right? Rules for insertion and removal. So remember, you can imagine a stack just like a stack of plates. So if I have my stack here, suppose I start off with an empty stack, so I don't have any elements yet. I can push elements onto my stack, but notice that if ever I want to remove an element, I pop it, right? I only get whatever's on the top of the stack. When I have no elements, I just return null. That's at least what we're going to presume here. So I imagine I push some elements onto the stack. So every time it goes onto the top of the stack, right? So whenever I do a pop, it's always popping the element on the top of the stack off, and we retrieve that. Note I also have some other operations, such as peek. I can peek at the top of the stack. I can stare at what it is. I don't remove it. I can just return what the element is, what the plate is storing. So I can just pop them like this. So that's what we talked about earlier on in the course, about a stack. So the idea with insertions and removals is that these are going to be your push operations, these are your pop operations. So it has the following operations. My apologies, that operations looks a little sad. It looked like it got melted. It was like out in the rain or something, and it got a little bit too wet. So remember, some of these I've defined for you already. I have push, so it adds an element. It adds an element E to the top of the stack. We had pop, which has no inputs. It removes and returns the top element of the stack. Or null if the stack is empty. I must stress that being empty means that there are no elements in the data structure, or in our container to be a bit more precise. If the stack is empty. As I mentioned, there is actually a few other operations that are very common. Peek. Some people call it top. Return. So it returns the top element of the stack. Of course, it returns or null if empty, right? If we don't have any elements, you just return null because the stack's currently empty. It has no elements. Also, we have size. It just returns the number of elements. So when we do our analysis and our discussion, this will be lowercase n. And we have is empty. So this asks the question, is the stack empty or not? So it returns whether the stack is empty or not. So if it is empty, it'll return true. If it is not empty, it returns false. So I'm going to talk about a couple of ways you can implement a stack. But one thing I do want to make a remark about, you'll find very often in my pseudocode, when I write out operations I apply to data structures, I usually use dot notation to do this. And I do this regardless if you would use an arrow or not in your implementation. You'll see this actually in some of my example code. So I mainly do this for two reasons. One, I like to just be consistent with you, but at the same time, if you're using some of the standard library containers, you'll just you often use a dot unless you dynamically allocate your data structure, because if you dynamically allocate it, you're going to use following some pointers. So for example, if I had a stack S, if I wanted to go, so my pseudocode, I'll very often go S, like if the stack's name is S, I'll have like stack, so I'll have S dot push, and say my element is called E. This is how I would very often write it for you. Or if I want to run execute is empty, you'll see I'll go S dot is empty. So this is me applying that operation. And of course, if some of them return a value, it's just like if you were to assign it. So for example, if I wanted to get the result of applying a pop operation, I have Y, I assign it s.pop. So this will just pop the stack and it returns me the element that was at the top of the stack, or null if it's empty. So I just want to make that little remark. This is just an aside. It's not really part of this definition. You'll find that I very often will write this way in my pseudocode for that reason. It's just to be consistent, and a lot of languages use the dots as opposed to dots versus arrows. So in C++, just know the difference when you're implementing. Say if you dynamically are allocating or building your own data structure, you'll very often be using arrows to apply the operations. But some things like the standard library, you'll be very often using just dots. So you'll get some exposure to this on the labs, for example. So let's walk through our first implementation. So naturally, I talked about arrays at the beginning. I'm going to talk about an array-based version of a stack. As I sort of alluded to near the beginning of the course, you can implement a stack using an array. So we would call that an array-based stack. Just like when we talked about a linked list-based stack. So we're going to have what I'm going to refer to as array stack. So the first of our two implementations I'm going to talk about here is the array stack. So it's just an array-based stack. And there's going to be a couple elements to this. Now, rather than going through and walking you through each one of these operations and writing out the algorithms, I'm going to include them in the notes. And I think it'll just be much easier for us to just kind of walk through what each one will do. So here's how we're going to go about this. We're going to maintain an array we're going to call stack. We maintain an array called stack. So that's its variable name. That's the name of the variable. With some capacity. With some capacity, capital N. To store elements. To store elements. We're going to maintain a counter called top that whenever we add 1 to it, it tells us how many elements there are in the stack. I'll call this top. So that if we add 1 to it, it's the number of elements, or the size of the stack. I must stress that this is initially top is assigned -1, which makes sense because if I have -1 and add 1 to it, I get 0, meaning the stack is currently empty. So that's actually one way you can easily just check if your stack is empty or not. So let's talk a little bit about how this gets represented. going to draw you a picture. And I think this picture will do a lot of explaining for me. So here's my array. I'm going to call it stack. It's going to have positions in it. It's going to have a whole bunch, possibly. It's going to have up to n slots in it, or n positions. So the last position will be indexed as position n minus 1. So I'm going to have the 0 indexed. And here's the thing. Whenever I put an element into the stack by pushing, I'm going to place it in a specific spot. So what's going to happen every single time I insert via a push operation, I'm going to increment that top counter by 1, and then I'm just going to place it into the spot for which you index with top. So for example, if top is currently -1, you know, right now it's empty, right? So if I do a push operation, I add 1 to it, and then I put it in the spot for which is top. So what you do is you increment top, and you put whatever your element is right there. So for the push operation, so I'll say assuming it fits, increment top by 1, and you just assign stack sub top to be whatever the element is. Stack sub top is assigned element E, for example. So this, if E is getting pushed, so like if I call it E, just like I have over there, then it goes into the spot for which, if you were to add 1 to it, it tells you how many there are. So when I start off with an initially empty array, I add 1 to -1, I get 0. And that'll tell you exactly where the top of the stack is. So presently, if I looked at my stack and I imagined it, presently it looks like this, where that's the top of the stack. So this top here is going to represent the top of the stack. So I could keep putting elements in, but the point is that whenever I push a new element in, say I push several elements in, whichever's the element on the top of the stack, suppose, I don't know, we'll call it T here. Suppose there's a whole bunch of elements that get pushed. Whichever that is, this will become the top of the stack, and it's represented by the counter top. So if you want to do a pop operation, you know exactly where it is actually. So if you do a pop operation, presuming it's not empty, so again, for all of the details for the written descriptions of these algorithms, look in the notes. I'm just trying to keep it brief for us because I think the idea is very natural to talk about. Assuming the stack is not empty, because if it is, then you know right away that you should probably just return null, right? You're just going to if it's not empty, keep track of stack sub top, right? Because that's currently the top of the stack. That's what this represents, this counter variable. You keep track of that. Then you decrement top, right? You decrement it by 1. Then return the top of the stack, right? So this specifically. So for example, if I wanted to do a pop operation, I wanted to get T, well, what would happen is I would keep track of this, I would hold on to this, and then I decrement top, and then I just return that. So if I do that pop operation, I get T, I hang on to it like some weird goblin, just like, it's mine. So it's not on here anymore, and then top gets moved over to the left by 1 position. because I just decremented it. Remember, this is just going to represent, this number represents the position that actually contains the top element. So naturally, if you ever need to do a peek operation, all you do is you just look at stack sub top, right? So assuming that stack, of course, isn't empty. If it's empty, you just return null. Getting the size, as I've already told you, you just simply add 1 to whatever top is, right? And of course, is empty, you just check you can always check the size and see if it's less than 0. Sorry, if you can always see that it is not going to be, yeah, it is less than 0 because it would be -1, right? Exactly. So believe it or not, these are actually the core pieces that make an array-based stack. So one last thing I wanted to talk about before I leave you here is, just as a quick remark, is the linked list based stack. We've actually talked about it already, so I have very few things to say about it. So I just thought I would quickly just walk you through that. So we'll talk about the time complexities of these operations probably next class. Just want to make a quick remark, a few remarks about the linked list based implementation of a stack, because we've talked about it during actually one of our first lectures. So I must note that there is an array-based version, an array-based implementation of the stack in the notes in C++. If you want to play around with it, it also includes an example of how you can resize the array. So this idea of expanding the capacity by increasing it, so when you run out of space in your array, it has an example of how this is done. Note that when you do the push operation in the array, if the array is full, you have to resize the array. There won't be space for it. So let me just make a quick couple remarks about the link stack. So the other common one is called the link stack. So we talked about this already. But I'm going to include more details here in the notes. But the idea is that you're just going to be maintaining a pointer that is going to be pointing at the node that contains the top element. So you might recognize this picture from a little while back. So you might call it top. And say I have elements here. Each one of my elements is stored in the node as the data attribute of the node in the linked list. And naturally, this represents the following. I have A, B, C, D like this. So if ever I want to push, I do an insertion of the linked list at the top, right? I do it right at the head of the linked list. So I will insert a new node here. If ever I want to do a pop operation, I just simply remove the first node of the linked list if it exists, and I return its contents, the data it has. Of course, delete the node after, because these are all dynamically allocated. One other detail is that normally when we want to maintain the size in this implementation, one thing I did not tell you I wanted to make a quick remark about is that we keep track of the number of elements, aka the size of this stack, using a counter variable. A counter variable, which I'll call count. And the idea is that it starts off at 0. So this begins as 0. So for example, if I have this representation, this would be that count is equal to 4 because there's 4 elements in the stack. So for the algorithms for all of these, I have them in the notes. Beyond that, I also included an example of how you might reverse an array using a stack. I'll come back to that next day, talking about some neat properties that stacks have. So that being said, I want to say thank you very much and have yourself a beautiful day. On to Q's tomorrow.